So, welcome back to our video lectures on projective geometry. We're still dealing with Cayley Klein Geometries, and you remember last time I showed you that along a line you get three different types of measurement in Cayley Klein Geometry depending on how this line intersects your fundamental objects. And this time I want to do the dual of that. I want to consider angle measurement. So in a certain sense, there's nothing new in that lecture today. It's just dualizing, but still I want to provide a kind of vivid image of how angle measurements look like in Cayley Klein geometry. So let me start with a little recap of what happened in last lectures. So we learned that whenever we have 2 points, they determine a line, and along that line you have a certain measurement in a Cayley Klein geometry, and the type of measurement depends on how that line intersects the fundamental object. So we have to distinguish three cases. One of the cases is the line intersects the fundamental objects in 2 points. The second case is it just touches the fundamental object, so this is kind of exceptional case. And the third case is it doesn't intersect the fundamental object in any real points at all. And depending on the situation in which we are, we get three different types of measurements. Here again, you see the pictures of walking in unit steps in one direction. So I start with a point here and I choose a certain distance, say the distance from the yellow to the blue point here, and then continue to walk in these unit steps. And you see in the hyperbolic case, what happens is that you walk in one direction and, well, from the outside of the geometry, so if you look at it from a bird's perspective where you see the fundamental conic, what happens is you will approach one of the intersections of the line with the fundamental conic. You will get closer and closer, but never surpass it. Somehow a little bit similar is the situation in the case where the line just touches the fundamental conic. There you also walk in unit steps in one direction, and here I put on that line the point of intersection at the point at infinity. So you will never surpass point at infinity, but independent whether you walk to the right or to the left, you will always end up with the same limit point. This is different from the hyperbolic case, where depending whether you walk to the right or to the left, you get either one or the other limit point. And last not least, we have the elliptic case where we don't have an intersection at all, so we don't have a limit point. So what happens is you walk in one direction and you go through infinity in a sense, but this infinity isn't named infinity in that case. So you go in one direction and eventually you will come back to where you started. And the same thing now from a dual viewpoint happens for angles. So you may have three different kinds of measurement. So what's the framework now? Now you have lines, and as we did measurements along a line in the case of distances, we will make measurements around a point for the angle case. So you have a point, and through that point you have many lines, and here again you have the case of adding angles of the same size in one direction, and if the point here is outside your fundamental object, you get two real tangents from the point to the fundamental object, and what happens in the distance measurement, you will approach this line but never surpass it, and if you go in the other direction, you will approach the other line. Pretty similar in the second case, the parabolic case, which is also sometimes called Euclidean measurement for reasons we will see later. So here, if you add unit angles in one direction, you will approach a limit line here, but if you go in the other direction, you will approach the same line here. And last not least, we get the elliptic angle measurement, where if you do angles in one direction, you at the end will, well, make a full turn around your point and end up where you started. It's like cutting pieces of cake from a cake, so at the end you will finally have cut the entire cake. So you should observe that this angle measurement that we have here is pretty close to what we have in our usual Euclidean geometry, and we will see that the pair of this distance measurement and this angle measurement makes up what we call our usual Euclidean geometry. So I want to give you a few pictures of that. So here are the different cases. Again, a little reminder, how did we formally calculate the angles between two lines? So we said, okay, if we have two lines and a fundamental object, then what I have to do to calculate the angle between these two lines is, first I have to calculate the point of intersection, then I have to draw two tangents to the fundamental object, then I have to take the cross ratio of those four lines, and this is possible because the lines were lines through the same point, and then I have to take the logarithm of that and multiply it by some constant c_ang, and later on I will say a little bit more about the constant. Just for the moment, still ignore it a little. So now we want to do an example, and I want to make this fundamental object to be a circle so that the pictures get a little bit more structure. So here I have the situation where the fundamental object is a circle, and here I have an animation where I again take unit steps, and you see what happens. You get this kind of measurement where you essentially approach one of the limit lines in one direction and you don't surpass it, and if you go in the other direction you approach the other limit line. And this is actually what happens if your point of intersection, the point around which you do the measurement, is outside the circle, because this is a dual situation of line cutting the circle. So in that case we get two real tangents. In the hyperbolic distance measurement case we got two intersections of the line. So let me move at least close to the situation where we are in the parabolic case. You see I moved my point very close to the circle, and now you see the effect that I told you, that these lines approach the same limit line, but again they will never surpass it. This is completely dual to what we had in the case of parabolic distance measurement. We went in one direction, approached that point at infinity, and if we went in the other direction we approached the same point. And last not least, we have the situation that this point here is inside the circle, so we don't get real tangents, and this means that we end up with an elliptic measurement where if you walk in unit steps in one direction, so you add the same angle in one direction, you at the end will end up where you started. So essentially you have your line and you add 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 and so on, and at the end you will end up in the same position of the line. So So you see, nothing new. It's really dual to what we did for the distance measurement. So I promised you to tell you at least a little about this constant C anc and the dual constant C dist that we have up here. And so far we almost in every slide ignored it more or less, and the reason for it is that it more or less has just a cosmetic reason. I usually call it the cosmetic constant. So the reason for this constant to be there is to make things in a way like we are used to it. So if you look at that picture here, you see that we have around that point here an angle measurement that looks very, very close to what we have as an angle measurement in Euclidean geometry. And so it would be nice to have this angle measurement in a way such that if we complete a full circle here, that the angles add up to a total of 2 pi. And to make this here like 2 pi is really the reason for this constants that we have here. So let's have a close look at the 3 different cases and how we calculate the angles in each way. So I sorted them in a way that I have first the hyperbolic case, then the elliptic case, and then the parabolic case. You should remember, in the first case we have 2 real tangents. Here we have only complex tangents, but they are complex conjugates, and here we have 1 tangent since we're just touching the fundamental object. So in our calculation of the angles, the x and y are different in all 3 cases. So in this case here, they are both real tangents and different. In the elliptic case, they turn out to be complex conjugates. So in both cases you have 2 degrees of freedoms. Here you have 2 real numbers, which gives you 2 real degrees of freedom. Here you have 2 complex conjugate numbers or tangents, which tells you, well, you have the degrees of freedom in one of them already because you have real and imaginary part, and the other one just follows by complex conjugacy. And in the last case, those 2 tangents really coincide. So let me see what happens if we do these calculations and start with the elliptic case. If these here are complex conjugates, what happens is that the cross ratio here ends up to be a complex number on the unit circle. Why is this so? We already had the calculation. So if you track down the calculation of the cross ratio to real numbers, what happens is you have the positions of L and M, which are somehow real, and you have X and Y, which are complex numbers and complex conjugates. So what happens is that up there and down here you have 2 complex conjugate numbers in the denominator and in the numerator, and if you divide one number by its own complex conjugate, what you get is a number on the complex unit circle. So this cross ratio here is a number on the unit circle. And now, since we are in the elliptic case, where the angle measurement looks very similar to what we had in our usual Euclidean case, and we want to make that to be something like 2 times pi, we have to compensate for that. And if you look at this constant here, we want to get back really this angle phi I've noted in here. So I have to get rid of this 2i as a constant. So what really happens is, if you take the logarithm of the cross ratio, then you get a number which is 2i phi, 2i times the angle between the lines, which is purely imaginary, and you get away the 2i if you choose the constant to be 1 divided by 2i. So a typical choice for the angle constant here is 1 divided by 2i, and this makes the measurement of the angles really look as we know it from Euclidean geometry. And you remember the formula of Laguerre, where I introduced you to the procedure of calculating the angle in Euclidean geometry. There x and conjugate x were played by I and j, and the formula of Laguerre was 1 divided by 2I times logarithm of cross ratio. So you see that really fits into the bigger picture. And for consistency reasons, you do essentially the same thing up here. So you have these two real numbers, you get a real cross ratio, which again splits into different cases. If this number here is real, then you get a real logarithm here, and if this number is negative, you get something like I times pi plus some constants d for distance, which really measures the distance. So actually the case that is relevant in practice is really the situation where you get the real numbers, which means that L and M are somehow not separated by your fundamental object. And so you see the calculations are pretty similar, and it's a good choice in that case to say, well, we get a real number and we just do this factor 1/2 here. So if we do 1 over 2I here and 1/2 here, we get a kind of consistency between those two cases. And in a sense, the irrelevant case is the parabolic angle measurement, because here the 2 points here, the 2 tangents are identical, so what you get is a cross ratio of 1, which results in a logarithm of 0, which somehow tells you that with respect to the ordinary Cayley Klein measurement, all angles here are really 0 in that case. And you remember in the distance case I talked 2 full slides about how to rescue that case by going to comparison of distances, and instead of taking that literally, just consider the relative lengths of two distances by comparing everything to a unit length, where you just end up with a kind of usual Euclidean distance measurement. Same happens here for the angle case. So now we learned that there are 3 types of distance measurement and 3 types of angle measurement. And now the question is, how do these things combine to make a kind of combined setup for measurements within geometry? And this is what our next lecture will be about. And in a certain sense, the next lecture is somehow the point in the lecture where we headed to all the way through our projective geometry class. In our next lecture, we will need everything we had so far to get the really big picture of what Cayley Klein geometries are, if you consider all of them. See you there!